Two massive sunspots, both aimed directly at Earth, both just unleashed powerful explosions, and right now, a wave of charged particles is racing toward us at millions of miles per hour. Something unusual is unfolding above us, and most people have no idea they're living through it. Stay with me for the next few minutes because we're going to uncover what these solar explosions mean for you, why scientists are watching these sunspots so closely, and what could happen when that invisible wave finally reaches our planet. You might think the sun is just that warm, predictable light in the sky. Rises every morning, sets every evening, constant, reliable. But that's only what we see from our fragile vantage point here on Earth. The reality is far more violent. The sun is a churning ball of nuclear energy, and right now, two powerful active regions are facing directly toward us. These aren't theoretical threats buried in academic papers. These are active, explosive regions on the solar surface, and they've already fired. The evidence is streaming toward us through space at this very moment, and when it arrives, you're going to feel it. Maybe not physically, maybe not consciously, but your world will respond. Your phone might struggle to find its location. Your GPS could drift by miles. Radio communications might crackle and fade. Airlines could reroute flights to avoid the chaos. Power grids across entire regions might strain under invisible pressure. And if you live far enough north, or even not so far north, you might step outside tonight and see something you've never witnessed before in your lifetime. Curtains of green and red light dancing across the darkness, the Aurora, nature's most beautiful warning sign. But here's what makes this moment different. It's not just one sunspot, it's two. And they're not firing randomly into space, spraying solar material in all directions like most eruptions do. No, these two regions are facing us, directly. They've positioned themselves, through the slow rotation of the sun, to aim their explosions precisely at our planet. Some might call it coincidence, others might call it cosmic timing, but whatever you call it, the result is the same. We're on the path. Now, before you close this video thinking I'm about to tell you the world is ending, let me be clear. That's not what this is. This isn't doomsday fear. This isn't conspiracy. This is science. This is real-time space weather, the kind of event that's happened before and will happen again. But it's also rare enough and powerful enough that when it does occur, we need to pay attention. Because our modern world, the one built on satellites and electricity and wireless signals, is far more vulnerable to the sun's activity than we like to admit. Think about it. Every technology you depend on, every convenience you take for granted, operates in an environment we barely understand. We've built a civilization on a planet wrapped in a magnetic field, and that field is the only thing standing between us and the full force of solar radiation. When the sun gets angry, when it throws massive clouds of charged particles our way, that magnetic shield bends, it strains, sometimes it breaks, and when it does, the consequences ripple through every system we've created. So what I want to do in this video is take you on a journey. We're going to explore these two sunspots together. I'm going to show you what they are, why they matter, and what's actually happening right now as that solar material races toward us. We'll talk about what could go wrong, sure, but we'll also talk about what's likely to happen. We'll separate the fear from the facts. We'll look at history, at the times the sun has struck before, and what we learned from those moments. And by the end, you're going to understand something most people will never grasp, that we live on a planet in motion, orbiting a star that's anything but calm, and that every single day we survive is a testament to the delicate balance of forces that make life possible. But I need you to do something for me right now. If this story has grabbed your attention, if you're curious about what's unfolding above us, hit that like button. It tells me you want more content like this. Real science, real events, explained in a way that makes sense. And drop a comment below telling me where you're watching from. I want to map out who's under this solar storm together. Are you in North America, Europe, Asia, Australia? Let's build a picture of this global moment, because that's what this is. This isn't happening to one country or one continent. This is happening to all of us together, under the same sun. And when that solar material arrives, we'll all be part of the same cosmic event. Subscribe if you haven't already, because as these sunspots continue to rotate and evolve, I'll be bringing you updates. This story isn't over. It's just beginning. So let's dive in and understand what's really happening up there. Let me introduce you to the two culprits. Scientists call them AR4324 and AR4325. Those aren't dramatic names. They're clinical catalogued identifiers assigned by solar observatories that track every significant feature on the sun's surface. But don't let the bland designations fool you. These two regions are anything but ordinary. They're vast, complex structures, each one large enough to swallow multiple Earths whole, And they've spent the last several days doing exactly what we hoped they wouldn't: growing, evolving, and erupting. Sunspots aren't holes in the sun. They're not dark patches of emptiness. They're regions where the sun's magnetic field has become so intensely tangled and concentrated that it suppresses the normal flow of heat from the interior. That makes them appear darker compared to the surrounding surface. But don't mistake darkness for coolness. These regions are still hotter than anything you could imagine on Earth. They're just cooler than the rest of the sun. And that temperature difference creates instability. Pressure builds, energy accumulates, and eventually something has to give. AR4324 appeared first, emerging on the sun's eastern limb as it rotated into view. Solar observers watched it grow, tracking its development through powerful telescopes and satellite instruments that stare at the sun without blinking. It's a complex region, which means it doesn't have a simple magnetic structure. Instead, it's a twisted mess of magnetic field lines, looping and crossing over each other in ways that create enormous tension. Imagine trying to twist a rubber band over and over again. Eventually it snaps. That's what happens in these sunspots, except instead of a rubber band, it's magnetic energy. And instead of snapping quietly, it explodes with the force of millions of nuclear bombs. AR4325 followed shortly after, rotating into view just as AR4324 was settling into a position facing Earth. Now we had two active regions, both with the potential to produce significant solar flares, both aimed at our planet. That alignment alone is noteworthy. The sun's surface is vast, and most eruptions fire their energy harmlessly into space, missing Earth entirely. But when an active region faces us directly, when it's positioned just right on the solar disk, that's when we start paying closer attention, because that's when the eruptions can hit us. And they did erupt, multiple times. Small flares at first, brief bursts of radiation that registered on monitoring equipment, but didn't pose serious threats. Scientists watched and waited. They analysed the magnetic structure of both regions, looking for signs of instability, trying to predict when the big one might come. And then, on the final day of last year, AR4324 delivered. A major explosion. Not the largest class of flare the sun can produce, but significant enough to send a shockwave through the space weather community. Alarms lit up at monitoring stations. Satellites recorded the burst of X-rays and ultraviolet light. And within minutes, solar physicists were analysing the data, trying to determine whether this eruption had launched a coronal mass ejection toward Earth. That's the question that matters most, because the flare itself, the burst of electromagnetic radiation, travels at the speed of light. It reaches Earth in just over 8 minutes. By the time scientists detect it, it's already arrived, already interacting with our atmosphere. But it's largely harmless to us on the surface. Our atmosphere absorbs most of that radiation, protecting us from the worst effects. Radio communications might experience brief disruptions. GPS signals could degrade temporarily. But nothing catastrophic. Nothing that fundamentally threatens our infrastructure. The real danger comes from what follows. If the magnetic structure of the sunspot is twisted just right, if the explosion is powerful enough and directed properly, it can hurl a massive bubble of plasma and magnetic field into space. That's a coronal mass ejection, a CME, and unlike the electromagnetic radiation from the flare, which dissipates quickly, a CME is physical matter. Billions of tons of charged particles ripped from the sun's corona and flung across the solar system at incredible speeds. When that hits Earth, it doesn't just pass through harmlessly, it collides with our magnetic field, it compresses it, distorts it, and sometimes it breaks through. So when AR4324 erupted, the immediate question was whether it had launched a CME in our direction. Scientists turned to their instruments, analysing images from satellites positioned between Earth and the Sun. They looked for the telltale signs: a bright expanding halo in coronagraph images, a shockwave rippling outward from the eruption site, evidence of material moving through space, and they found it. A CME was launched. Not a glancing blow that would barely brush past Earth's magnetic field. This one was headed more directly toward us. But AR4324 wasn't finished. It erupted again with another significant flare, another release of energy. And AR4325 also showed increased activity during this period. Now both regions were active simultaneously, with AR4324 confirmed to have fired explosions toward Earth, and both regions potentially launching their own CMEs. It's one thing to track a single solar storm. It's another entirely to track multiple storms from different regions, each with its own speed and trajectory, each potentially arriving at Earth at different times. The complexity multiplies, the uncertainty grows, and the potential for unexpected interactions between the storms increases. This is what solar scientists mean when they talk about complex space weather events. It's not just about one sunspot doing one thing, it's about multiple active regions, multiple eruptions, multiple CMEs all happening within a short time window, all directed toward the same target: us. And while Earth has survived countless solar storms throughout its history, each one is different. Each one teaches us something new, and each one carries the potential to surprise us. What makes AR4324 and AR4325 particularly interesting beyond their Earth-facing positions is their timing. We're currently in an active phase of the solar cycle, that roughly 11-year pattern of increasing and decreasing solar activity. The Sun is approaching its maximum, the peak of this cycle when sunspots are most numerous and solar eruptions are most frequent. That means we're entering a period where events like this become more common, more sunspots will emerge, more flares will erupt, more CMEs will launch toward Earth. This isn't a one-time occurrence, it's a preview of what we can expect over the coming months and possibly years. But even within that context of increased activity, having two significant active regions simultaneously facing Earth during a period of heightened activity stands out. It's not unprecedented, it's happened before, but it's rare enough that it commands attention. Solar physicists are watching these regions closely, tracking their evolution, monitoring for additional eruptions. Because sunspots don't just erupt once and disappear, they can remain active for days or even weeks, producing multiple flares and CMEs as they rotate across the Sun's face. As long as AR4324 and AR4325 remain visible from Earth, as long as they continue facing us, scientists will continue monitoring them for additional activity, and that brings us to the present moment, to right now as you watch this. Those CMEs launched from both regions over the past several days are travelling through space toward us. They've already crossed vast distances, they're already closer to Earth than they were when this video began, and sometime very soon, possibly within hours or days of you hearing these words, they're going to arrive. They're going to collide with Earth's magnetic field, and when they do, we're going to see what happens when our technology meets the Sun's activity. So now that you understand these active regions, let's talk about what they've launched and why it matters. Here's what most people don't understand about solar explosions. There are actually two separate threats, and they arrive at different times in different ways: the flare and the coronal mass ejection. Most people hear those terms and assume they're the same thing, just different names for the same event, but they're not. They're distinct phenomena, each with its own characteristics and dangers, and understanding the difference is crucial to understanding what's happening right now. Let's start with the flare. When a sunspot's magnetic field becomes too twisted, too stressed, it suddenly releases that built-up energy in a massive explosion. That explosion primarily takes the form of electromagnetic radiation, X-rays, ultraviolet light, radio waves. It's like the sun suddenly cranks up its brightness in wavelengths we can't see with our eyes. All that radiation streams away from the sun in every direction at the speed of light. Nothing in the universe travels faster, so if the flare happens on the side of the sun facing Earth, we're bathed in that radiation just over 8 minutes later. There's no warning, no time to prepare. By the time we detect it, it's already here. But here's the key thing about flares. For us on Earth's surface, they're almost entirely harmless. Our atmosphere is thick enough and protective enough to absorb that incoming radiation before it reaches us. We don't feel it, we don't see it. We go about our day completely unaware that we just survived what would have been a lethal dose of radiation in space. The atmosphere shields us perfectly. Where flares do cause problems is in the upper atmosphere and beyond. Radio waves that travel through the ionosphere, that layer of charged particles high above us, can be disrupted. Communications that depend on bouncing signals off the ionosphere can fail. GPS satellites orbiting above the protective atmosphere experience increased drag and radiation exposure, but again, these are technical problems, not existential threats. So if flares are relatively manageable, why all the concern? Because flares are often the warning shot. They're the sign that a sunspot is releasing enormous energy. And sometimes, when the conditions are just right, that energy release doesn't just radiate outward as light. Sometimes it physically rips material away from the sun itself. That's the coronal mass ejection, the CME, and that's where things get serious. Imagine the sun as having an atmosphere, just like Earth does. We call it the corona, that faint halo of light you can see during a total solar eclipse. It's unimaginably hot, actually hotter than the sun's surface, one of the great unsolved mysteries of solar physics, and it's not static. It's constantly moving, churning, following the twisting magnetic fields that extend out from the sun. When a sunspot erupts powerfully enough, it doesn't just send out radiation, it launches a bubble of that coronal material into space. Billions of tons of plasma, hot ionized gas threaded with magnetic field lines, all hurled outward at speeds that can reach millions of miles per hour. This is physical matter. It's not light that passes through space and dissipates. It's a cloud, a wave, a tsunami of charged particles that travels across the solar system. And unlike the radiation from a flare, a CME takes time to reach Earth. The fastest ones can arrive in less than a day. The slower ones might take several days. That difference in arrival time is actually our saving grace, because it means we get warning. When satellites detect a CME launch, we can calculate its speed and trajectory. We can predict when it will reach Earth. We can prepare. But prepare for what? That's the question everyone asks. What actually happens when billions of tons of solar plasma collide with our planet? Do we feel it? Does it hurt us? The answer is complicated because it depends on several factors. First, the CME has to actually hit us. Remember, space is vast and Earth is tiny. Most CMEs miss us entirely, sailing past into the deeper solar system without ever interacting with our planet. Even when a CME is aimed in our general direction, slight variations in speed or trajectory can mean the difference between a direct hit and a complete miss. Second, not all CMEs are created equal. Some are weak and diffuse, carrying relatively little energy. Others are dense and fast, packed with intense magnetic fields and enormous numbers of particles. The stronger the CME, the more intense its effects when it reaches Earth. And third, the orientation of the CME's magnetic field matters enormously. Earth has its own magnetic field, and when a CME arrives, the two magnetic fields interact. If they're aligned the same way, the interaction is relatively gentle. The CME mostly slides around Earth's magnetic field like water around a rock. But if they're oriented opposite to each other, if the CME's magnetic field points south while Earth's points north, then they connect. They merge. And that allows the solar plasma to penetrate much deeper into Earth's magnetic environment. That's when we get geomagnetic storms. That's when the real effects begin. The incoming solar particles don't just bounce off our magnetic field. They get channeled along the field lines, funneled toward the polar regions where the magnetic field lines converge. They slam into our atmosphere, exciting atoms and molecules, causing them to glow. That's the aurora, the northern and southern lights. It's beautiful, yes, but it's also a visible sign of our planet interacting with solar material. It's proof that solar particles have penetrated our defenses and are pouring energy directly into our atmosphere. And here's what makes our current situation notable. When scientists analysed the CMEs launched by AR4324 and AR4325, they determined these weren't minor events. These weren't weak, glancing blows. Initial models suggested these CMEs had significant density and speed. They were aimed at least partially toward Earth, and while predicting the exact magnetic field orientation of a CME is difficult until it actually arrives, the potential was there for strong geomagnetic activity when they reached us. Now, I need to pause here and address something important. You might be hearing terms like G1, G2, maybe even G3 storm levels in the news or on space weather websites. These are classifications that describe the strength of geomagnetic storms, ranging from G1, which is minor, all the way up to G5, which is extreme. The early predictions from NOAA for these particular CMEs suggested G1 to G2 conditions for January 13th, 2026. That's minor to moderate. It's not catastrophic. It's not the kind of event that shuts down continents, but it's significant enough to warrant attention, especially for certain vulnerable systems. At G1 levels, we might see weak power grid fluctuations, minor impacts on satellite operations, aurora visible at higher latitudes. Most people wouldn't notice anything unusual. At G2, the effects intensify. Power systems at high latitudes might require voltage corrections. Satellites could experience increased drag affecting their orbits. Aurora might be visible at mid-latitudes, much farther south than normal. Radio communications, particularly high-frequency signals used by aircraft and ships, could experience disruption. But here's what you need to understand about these classifications. They're forecasts, not certainties. Space weather prediction is incredibly difficult because we're trying to model the behavior of plasma and magnetic fields across millions of miles of space. We can't measure the CME directly until it reaches satellites positioned between Earth and the Sun, and by then it's less than an hour away. So the predictions we get days in advance are educated guesses based on observations of the eruption itself. Sometimes they're accurate, sometimes the storm is weaker than expected, and sometimes, rarely, it's stronger. What makes a CME truly dangerous isn't necessarily its size or speed, it's the combination of factors. A fast, dense CME with a strongly southward-pointing magnetic field arriving during a time when Earth's magnetic field is already disturbed by previous activity. That's when we get the extreme events. That's when power grids actually fail. That's when satellites are damaged or lost. That's when we see effects that last for days or weeks. The worst geomagnetic storm in modern history, the one everyone in the space weather community references, happened when multiple factors aligned perfectly for disaster. And that's what scientists watch for now. Not just individual CMEs, but the potential for multiple storms to compound each other's effects. With AR4324 and AR4325 both erupting within a short time frame, there's at least the possibility that multiple CMEs could arrive at Earth close together. If the first one disturbs our magnetic field, compresses it, leaves it in a weakened state, and then the second one hits before the field has recovered, the effects could be amplified. It's like getting hit while you're already down. Your defenses are compromised. You're more vulnerable to damage. That's the scenario scientists were monitoring as these CMEs raced toward us. But let's be clear about something else. The term storm in geomagnetic storm can be misleading. It's not a weather storm. There are no clouds, no rain, no wind that you can feel. The storm is happening in near-Earth space, in the region where our magnetic field interacts with the incoming solar wind. For most of human history, these storms happened regularly and no one knew. No one noticed. Life continued normally. It's only because we've built a technological civilization dependent on electricity, satellites, and radio signals that these invisible storms now matter. The danger isn't to our bodies, it's to our infrastructure, to the systems we've come to depend on absolutely. So as those CMEs approached Earth, carrying their cargo of charged particles and twisted magnetic fields, scientists around the world were watching, monitoring, calculating, trying to determine exactly when they would arrive and what would happen when they did, and that's where we need to go next. Because a CME isn't a single event that happens and ends. It's a journey across space, a race against time. And right now that race is nearly over. Right now, as you hear these words, those CMEs are somewhere between the Sun and Earth. They've been travelling for hours or days depending on exactly when you're watching this. They've crossed tens of millions of miles, and they're closing in on our planet with every passing second. There's something profound about that, isn't there? An invisible phenomenon travelling through space, which we can monitor and prepare for. We can only watch, wait, and prepare for whatever happens when it arrives. The journey of a CME is unlike anything else in our experience. We're used to things that move slowly enough to track with our eyes, or so fast they arrive instantly. But a CME exists in this strange middle ground, fast enough that it crosses the distance from Sun to Earth in a matter of days, but slow enough that we can watch its progress, counting down the hours until impact. It's cosmic timescale, but just barely within our ability to comprehend. When the eruption first happened, when AR4324 and AR4325 threw their material into space, that plasma left the Sun travelling at incredible speeds. Not all CMEs move at the same velocity. Some are relatively sluggish by cosmic standards. Others are among the fastest things we've ever observed moving through the solar system. The speed depends on how much energy the eruption contained, how much force was behind the launch. Think of it like throwing a ball. Throw it gently and it arcs slowly. Throw it with all your strength and it rockets forward. The Sun's eruptions work on similar principles, just with scales that boggle the mind. The CMEs from these sunspots were classified as moderately fast. Not the record-breaking velocity that would bring them screaming into our magnetic field in less than a day, but fast enough to arrive within the typical window scientists were monitoring. And as they travelled, they weren't moving through a vacuum. Space between the Sun and Earth isn't empty. It's filled with the solar wind, that constant stream of particles flowing outward from the Sun in all directions. A CME is like a shockwave moving through that wind, pushing it aside, compressing it, creating a disturbance that propagates outward. Scientists track CMEs using a fleet of satellites positioned at strategic locations. Some orbit Earth, watching the Sun constantly for signs of eruptions. Others sit at a special point in space called L1, a location between Earth and the Sun where gravitational forces balance out. A satellite at L1 can stare at the Sun while remaining in a fixed position relative to Earth. It's the perfect vantage point for space weather monitoring. When a CME erupts, these satellites see it first. They watch it expand outward from the Sun. They measure its speed and estimate its direction. But here's the challenge. From Earth's perspective, looking at the Sun, a CME that's headed directly toward us appears different from one that's headed off to the side. A CME aimed right at us looks like an expanding halo around the eruption site, growing larger, but not moving to the left or right. That's because it's coming straight toward the observer. It's the same perspective issue that makes it hard to judge if a car is moving toward you or away from you when you're looking at it head-on. You need side view information to be certain. That's where models come in. Scientists feed observations into sophisticated computer simulations that attempt to recreate the CME's journey through space. They input the estimated mass, the measured speed, the direction indicators from satellite imagery. The models then calculate a predicted trajectory and arrival time. They show whether the CME will hit Earth directly, deliver a glancing blow, or miss entirely. But these models aren't perfect. They're approximations based on limited data. The actual arrival time can vary by hours. The impact strength can be stronger or weaker than predicted. As the CMEs from AR4324 and AR4325 travelled through space, those models were running continuously, updating as new data came in. Early predictions suggested arrival times in the days immediately following the eruptions. Scientists issued watches and warnings to power grid operators, satellite companies, airlines, anyone who might need to take precautions, and then came the waiting. That strange period where you know something is coming but can't do anything except prepare and watch. This is where space weather forecasting differs fundamentally from Earth weather forecasting. With a hurricane, you can track it with radar and satellites, watch it approach hour by hour, see the spiral bands and the eye. You get visual confirmation of the threat. With a CME, you're tracking something invisible. You launched it days ago based on observations of an eruption. You've estimated its path and speed. But until it reaches those monitoring satellites at L1, until it's less than an hour from Earth, you don't have direct confirmation of its properties. You don't know for certain how strong the magnetic field is inside it, whether it's still coherent or has dispersed, whether your predictions were accurate. That's the position scientists were in as these CMEs approached. They had done all the analysis they could. They had made their predictions, they had issued appropriate alerts, and now they were watching the data streams from L1, waiting for the first signs that the CMEs had arrived at the monitoring satellites, waiting for that final confirmation, waiting to see if their predictions were right. There's another factor that complicates this journey. CMEs don't travel through space like bullets, maintaining a fixed speed and trajectory. They interact with the solar wind. They can be accelerated or decelerated depending on the conditions they encounter. If they're moving faster than the ambient solar wind, they create a shockwave ahead of them, and that shockwave can trigger effects even before the main body of the CME arrives. If multiple CMEs are launched in sequence, they can catch up to each other, merge, create combined storms that are more powerful than either individual event would have been. That possibility existed here. With both AR4324 and AR4325 erupting within a relatively short time window, their CMEs were travelling through the same region of space. They might arrive at Earth separately, hours or days apart, or they might interact during their journey, creating a more complex event. The uncertainty is part of what makes space weather so challenging. We're observing dynamic, evolving phenomena across distances so vast that light itself takes minutes to cross them. But regardless of the exact details, the fundamental reality remained unchanged. Those CMEs were coming. They would reach Earth, and when they did, our planet's magnetic field would respond. The only questions were exactly when and exactly how strong the impact would be. So while scientists monitored the incoming storms, let me take you back in time, because Earth has been hit by solar storms before, many times, and understanding what happened in the past gives us crucial context for what might happen now. September 1st, 1859. Most people alive that day had no idea anything unusual was happening. The sun rose, the day began, life in the mid-19th century continued at its normal pace. But something extraordinary was unfolding in the heavens, something that would, within hours, create effects so dramatic that people alive in the southern United States would see Aurora dancing overhead. Telegraph operators would report their equipment sending messages without any battery connected, and one amateur astronomer in England would witness an event that would carry his name through history. Richard Carrington was observing sunspots that morning, projecting an image of the sun onto a screen in his private observatory, carefully sketching the features he saw. It was routine work, careful documentation, the kind of patient science that builds knowledge slowly over years, and then suddenly it wasn't routine anymore. Carrington watched as an intensely bright flash appeared within one of the sunspot groups he was observing. It lasted only minutes, but it was so bright, so energetic that he could see it even in the overwhelming glare of the sun's surface. He knew immediately he was seeing something rare, something significant. He had no idea he was watching a solar flare of extraordinary power. The term solar flare hadn't even been invented yet. But he had witnessed the eruption, and less than 24 hours later, the CME from that explosion arrived at Earth. The speed suggested it was one of the fastest on record, a storm racing across space at exceptional velocity. When it hit, The effects were immediate and stunning. The aurora that night was visible as far south as the Caribbean, in Cuba, in Hawaii, places where the northern lights had never been seen in human memory. The sky glowed red and green. People thought cities in the distance must be on fire. They woke their neighbours, some prepared to evacuate, but there was no fire. It was the aurora, driven to impossible latitudes by the intensity of the geomagnetic storm. Telegraph systems, the cutting-edge technology of that era, went haywire. Operators reported receiving severe electric shocks from their equipment. Some telegraph lines continued operating even after operators disconnected the batteries, powered solely by the electrical currents induced in the wires by the fluctuating magnetic field. Messages were sent and received using only the power provided by the geomagnetic storm itself. In other locations, telegraph equipment caught fire, sparks flew, systems failed completely. This was the Carrington Event, the most powerful geomagnetic storm in recorded history, and here's what makes it so relevant to our discussion today. If an identical storm struck Earth now, in our modern technological age, the consequences would be severe and widespread. Not because the storm itself would be any more physically powerful, the sun doesn't care what century it is, but because we've built a civilization that's exquisitely vulnerable to exactly the kind of effects that storm produced. Consider what existed in 1859. Telegraph lines were the extent of our electrical infrastructure. That was it. No power grids, no satellites, no GPS, no computers, no internet. The telegraph network was impressive for its time, but it was a tiny fraction of our current technological dependence. When the Carrington Event struck, it damaged that limited infrastructure, but society continued functioning. Messages couldn't be sent by telegraph for a while. That was unfortunate, but life went on. Now imagine the same storm today. Those same intense electrical currents induced in wires by the violently fluctuating magnetic field wouldn't just flow through telegraph lines. They would flow through high-voltage power transmission lines spanning continents. And here's the critical difference. Modern power transformers, those huge pieces of equipment that step voltage up and down throughout the electrical grid, are not designed to handle direct current. They're built for alternating current, the kind that oscillates back and forth at a fixed frequency. When you force direct current through a transformer designed for AC, it saturates, it overheats. And if the current is strong enough and lasts long enough, it fails catastrophically. A transformer failure might not sound dramatic, but these aren't devices you can replace quickly. Large power transformers are custom-built pieces of equipment. They can take months or even years to manufacture. They're transported on special trucks because of their size and weight. A major geomagnetic storm could damage or destroy transformers across a wide geographic area simultaneously, and replacing them would be a significant logistical challenge requiring years of coordinated effort. In 1989, we got a small preview of what this might look like. A geomagnetic storm significantly less powerful than the Carrington Event struck Earth. It wasn't remotely in the same category of intensity, but it was enough to cause problems. In Quebec, Canada, the power grid collapsed. 6 million people lost electricity. In March, in a region where temperatures in March can still be well below freezing. The outage lasted hours, but it demonstrated the vulnerability. Transformers overheated, protection systems failed, the grid went down. That was a moderate storm. A Carrington-level event would be orders of magnitude stronger. Studies conducted by government agencies and research institutions have attempted to model what would happen if such a storm struck today. The results are sobering. Widespread, long-duration power outages affecting potentially tens of millions of people. Satellite damage or loss, affecting GPS navigation, communications, weather forecasting, military operations, high-frequency radio blackouts grounding flights and disrupting maritime communications, economic costs that could reach into the trillions over the years needed for recovery. And here's the unsettling part. A Carrington-level event isn't some theoretical maximum that the sun might achieve under extreme circumstances. It's something that actually happened. Recently, in cosmic terms, less than 2 centuries ago. The sun has done it before, and solar physics tells us the sun is fully capable of doing it again. In fact, we've found evidence in ice cores and tree rings that even more powerful storms have struck Earth in the more distant past. Events that happened long before human civilization had any technology to damage, but that left their signature in the geological record. One event in particular stands out. It happened around the year 775, more than 1,000 years ago. Scientists discovered it by analysing the concentrations of certain radioactive isotopes in tree rings and ice cores from that year. The spike in these isotopes indicates Earth was bombarded by a massive flux of high-energy particles from the Sun. The estimated intensity of this event exceeds anything we've observed in the modern era. It dwarfs the Carrington Event, and it's a stark reminder that the Sun's energy output capability exceeds even our most extreme historical examples. But let's come back to more recent times. The October 2003 Halloween storms, a series of powerful eruptions from an enormous sunspot group, produced multiple X-class flares and CMEs. Some hit Earth. The geomagnetic storms that resulted damaged satellites, disrupted power systems in Sweden, and caused widespread aviation rerouting. The Aurora was visible across North America, much farther south than normal. It was a complex multi-day event that tested space weather forecasting capabilities and demonstrated our ongoing vulnerability. Then in July 2012, something extraordinary happened. A Carrington-class CME erupted from the Sun and raced through Earth's orbit. If it had erupted 1 week earlier, it would have hit us directly. Instead, it missed Earth completely. We detected it only because satellites positioned elsewhere in the solar system passed through the region where it occurred. Analysis of that CME's properties confirmed it was comparable in strength to the Carrington event. We dodged it purely by chance, by the timing of Earth's position in its orbit. That near miss was a wake-up call for many in the space weather community. These extreme events aren't ancient history. They're ongoing threats that we avoid mostly through luck. More recently, we've seen increased solar activity as the Sun approaches its current cycle maximum. Multiple strong geomagnetic storms have occurred. Aurora has been visible at unusually low latitudes. Each event provides more data, more understanding, but also more evidence of our vulnerability. And each event reminds us that space weather isn't a curiosity or an academic topic. It's a real, present, ongoing interaction between our star and our planet that has consequences for the technology we depend on. The historical record teaches us several crucial lessons. First, major solar storms are not rare in an absolute sense. They happen. Not every year, but regularly enough that experiencing multiple events in a human lifetime is entirely possible. Second, our vulnerability to these storms has increased dramatically as our technological dependence has grown. Third, the most extreme events can produce effects that are difficult to predict in advance because they exceed our experience base. We've never experienced a Carrington-level event with our modern infrastructure in place. We're modelling and estimating, but we won't know for certain what would happen until it happens. And that brings us to a crucial question. Where do the current CMEs from AR4324 and AR4325 fit in this historical context? They're not Carrington-level events. Early predictions suggested minor to moderate geomagnetic activity, nothing catastrophic. But they're also not insignificant. They represent the kind of solar activity we should expect to see more of as the Sun's cycle progresses. They're tests of our systems, probes of our defences, and they're reminders that Earth doesn't exist in isolation. We orbit a star that's anything but stable, and that star regularly hurls material in our direction. So with that historical context in mind, with the understanding that Earth has survived massive solar storms before, but is now more vulnerable than ever, let's talk about the one thing standing between us and those incoming CMEs. Let's talk about Earth's magnetic shield, and what happens when solar storms try to breach it. You can't see it, you can't feel it. Most of the time you're not even aware it exists. But right now, as you go about your day, as you move through your life, you're protected by an invisible force field that extends thousands of miles into space. It's Earth's magnetosphere, the magnetic field generated by currents of molten iron flowing in our planet's outer core. And it's the only reason life exists on this planet's surface. Without it, the Sun's radiation would strip away our atmosphere. Solar particles would bombard the surface directly. Earth would be a barren, irradiated rock like Mars. The magnetosphere is literally what makes life possible, but that protection has limits. The magnetic field is strong, yes, but it's not impenetrable. It's more like a bubble than a solid wall. When the solar wind, that constant stream of particles from the Sun, encounters Earth's magnetic field, it doesn't just bounce off. It compresses the field on the day side, the side facing the Sun, squeezing it inward. On the night side, away from the Sun, the field is stretched out into a long tail that extends far into space. The whole structure is dynamic, constantly shifting and responding to changes in the solar wind. Under normal conditions, when the Sun is relatively quiet, this system is stable. The solar wind applies steady pressure. The magnetic field holds its shape. Particles are deflected around Earth, flowing past us like water around a rock in a stream. Most of the solar wind never reaches our atmosphere. It's guided around us by the magnetic field lines and continues on into deeper space. This has been happening for billions of years. It's why Earth retained its atmosphere while Mars lost most of its own. But a CME isn't normal solar wind. It's not a steady stream. It's a shock wave, a wall of plasma and magnetic field travelling much faster and carrying far more energy than the background solar wind. When a CME collides with Earth's magnetosphere, everything changes. The pressure on the day side increases dramatically. The magnetic field is compressed even further, pushed inward toward the planet, and if the CME's magnetic field is oriented opposite to Earth's, if south meets north in that collision, then something called magnetic reconnection occurs. Reconnection is one of those terms that sounds technical, but describes something fundamentally violent. When magnetic field lines of opposite orientation come together, they can break and reconnect in new configurations, and when that happens, energy is released, enormous amounts of energy. The magnetic field lines snap like rubber bands, particles are accelerated, and suddenly there's a pathway for solar material to penetrate deeper into Earth's magnetic environment than it normally could. That's when we get a geomagnetic storm. That's when the effects begin cascading through our planet's magnetic field. Particles that should have been deflected instead get funneled along field lines toward the poles. They spiral down toward Earth's atmosphere, following the magnetic field lines that converge at the north and south magnetic poles. And when those high-energy particles slam into atmospheric molecules, they transfer their energy, exciting atoms and causing them to emit light. That's the aurora. It's not just beautiful, it's visible proof of solar particles following magnetic field lines into our atmosphere, a natural process the magnetosphere is designed to handle. Now, the classification system for geomagnetic storms exists to help us understand and prepare for these events. The scale runs from G1, which is minor, up to G5, which is extreme and rare. Each level corresponds to a certain intensity of disturbance in Earth's magnetic field, measured by ground-based magnetometers around the world. At G1, the effects are subtle. Power grids might experience weak fluctuations. Aurora might appear at high latitudes, nothing unusual for places like Alaska or northern Canada. Satellite operations might require minor corrections. Move up to G2, moderate storm levels, and things get more interesting. Power systems at high latitudes might require voltage corrections to prevent problems. Satellites in low Earth orbit experience increased atmospheric drag, which can affect their trajectories. Aurora becomes visible at mid-latitudes, appearing in regions where it's usually not seen. High-frequency radio communications can be disrupted. Planes flying polar routes might need to reroute to maintain reliable communications. G3 storms bring widespread effects. Power systems might need voltage corrections applied in multiple locations. Satellites could experience surface charging and increased drag requiring operational adjustments. Aurora visible at even lower latitudes. Radio communications degraded for hours. GPS systems experiencing errors. This is where we start seeing effects that impact a broader segment of the population, not just specialized systems in specific locations. G4 and G5 storms are where things get serious. Widespread voltage control problems in power grids. Protective systems might trip unnecessarily, causing outages. Satellites could be damaged or their operations significantly impacted. Radio communications severely disrupted for extended periods. GPS unreliable. Aurora visible at very low latitudes. G5, the extreme category, is where we'd expect to see effects comparable to historical major storms. Long-duration outages possible. Satellite damage likely. Communications blackouts. The kind of event that dominates headlines and has real economic consequences. When scientists analysed the CMEs from AR4324 and AR4325, their initial assessment suggested we were looking at G1 to G2 conditions, minor to moderate, not catastrophic, not a repeat of Carrington or the Halloween storms, but still significant enough to warrant watches and warnings, still enough to potentially cause disruptions in vulnerable systems, and with the possibility of multiple CMEs arriving close together, there was at least some chance of the effects being amplified beyond what either individual storm would produce. The watches were issued. Power grid operators were notified to monitor their systems more closely. Satellite companies were advised to take precautions. Airlines received updates about potential high-frequency radio disruptions, and the Aurora forecasting community started getting excited because G1 to G2 storms often produce aurora visible well south of the Arctic Circle. People who never get to see the northern lights might have an opportunity. But here's what's important to understand. These classifications, these predictions, they're our best estimates based on available data. The actual storm could be weaker, it could be stronger. We won't know for certain until the CMEs arrive, and we measure their properties directly at the L1 monitoring satellites. And even then, the effects can vary. Two storms with similar measured properties can produce different results depending on factors we don't fully understand. Earth's magnetic field itself isn't constant. It varies over time. It can be in different states of stability or instability when a CME arrives. That initial state affects how the magnetic field responds to the incoming solar material. Think of it like a person's immune system. The same virus might cause a mild cold in one person and severe illness in another, depending on the state of their immune system at the time of infection. Earth's magnetosphere works similarly. The same CME might produce a minor storm if Earth's magnetic field is stable and well configured, or it might produce a stronger storm if the field is already disturbed from previous activity. That's part of what makes space weather forecasting so challenging. We're not just predicting the properties of the incoming storm, we're trying to predict how Earth's dynamic magnetic system will respond to that storm. So as those CMEs approached, as they crossed the final millions of miles between the Sun and Earth, the space weather community was in a state of heightened awareness. Monitors watching, data streaming in, models updating, everyone waiting to see what would actually happen when solar storm met planetary defense. Would the predictions hold? Would the storms be weaker or stronger than expected? Would Earth's magnetic field hold firm, or would it bend and buckle under the assault? And for those of us on the surface going about our daily lives, most of it would be invisible. We might notice our phone's GPS acting strangely. We might hear reports of radio disruptions. If we were paying very close attention to our lights, we might notice subtle flickers as power systems responded to fluctuations. But mostly, we'd be unaware of the dynamic interaction happening above us. That billions of tons of solar plasma were colliding with our magnetic field thousands of miles above us. That invisible forces were wrestling in near-Earth space. Our ignorance is a testament to how well the magnetosphere does its job, even under assault, and it's a reminder that the universe is far more active and dangerous than our daily experience suggests. We live in a bubble of protection that we barely acknowledge and rarely appreciate, at least until something goes wrong. So let's talk about what could go wrong. Let me walk you through a scenario, not to frighten you, but to help you understand how interconnected our modern world is, and how a disturbance in one system can cascade through many others. Imagine a geomagnetic storm stronger than the current predictions, not Carrington level, but solidly in the G3 or G4 range. Enough to push systems beyond their comfort zones. What happens? It starts in space. Satellites orbiting Earth are outside the protective atmosphere, exposed directly to the incoming solar particles. These particles carry electrical charge, and when they strike satellite surfaces, they can cause surface charging. Think of it like building up static electricity, except on a spacecraft traveling through a hostile environment. If enough charge builds up, it can arc across components, damaging electronics. It can confuse sensors. It can cause satellites to lose their orientation, their understanding of which way they're pointing. A satellite that loses orientation can't point its solar panels at the Sun, which means it can't generate power. It can't point its antennas at Earth, which means it can't communicate or relay signals. For a communication satellite, that's catastrophic. Thousands of customers suddenly lose service. For a GPS satellite, it means the navigation signals it broadcasts become unreliable or disappear entirely. And we have dozens of satellites that provide GPS coverage. If several of them have problems simultaneously during a geomagnetic storm, the entire GPS system's accuracy degrades. Now think about who uses GPS. You do, obviously, when you're navigating to an unfamiliar location. But GPS is embedded in systems you probably don't think about. Precision agriculture uses GPS to guide tractors within inches of their intended path. Shipping and logistics companies use GPS to track containers and optimize routes. Airlines use GPS as part of their navigation systems. Cell phone towers use GPS timing signals to coordinate their operations. Financial trading systems use GPS timestamps to sequence transactions. The electrical power grid itself uses GPS time signals to synchronize operations across vast distances. What happens when GPS accuracy degrades or signals become unreliable? Those systems start having problems. Small errors accumulate. Timing gets slightly out of sync. Maybe it's not enough to cause immediate failures, but it's enough to force fallback modes, backup systems, manual interventions. Efficiency decreases, costs increase, and if the storm is strong enough and lasts long enough, some systems start failing altogether. Meanwhile, back on the ground, power grid operators are watching their monitoring systems with increasing concern. Those induced currents I mentioned earlier, the geomagnetically induced currents or GICs, are flowing through the high-voltage transmission lines. These currents aren't huge. They're not like lightning strikes delivering massive instantaneous power. They're relatively small currents, but they're direct current, and they persist for as long as the geomagnetic storm lasts. That could be minutes, it could be hours. Transformers experiencing GIC start operating outside their design parameters. Internal components heat up. Cooling systems work harder. In most cases, the transformers handle it. That's what they're built to do. But transformers aren't designed for this kind of stress. They're designed for alternating current at specific voltages and frequencies. GIC represents operation outside design parameters, and like any equipment operating beyond specifications, there's a risk of damage. If a transformer overheats sufficiently, its protection system should trip, disconnecting it from the grid to prevent catastrophic failure. That's the designed response. But when transformers start tripping across a wide area, the grid has to compensate. Power that was flowing through the disconnected transformer has to be rerouted. Other transformers have to carry more load, and if too many transformers trip too quickly, the grid can't compensate fast enough. That's when you get cascading failures. That's when the lights go out. A major blackout during a geomagnetic storm would be unlike a typical power outage. In a normal situation, when a storm knocks down power lines, or a tree falls on a transformer, utility crews can assess the damage and begin repairs. But during a geomagnetic storm, you can't just restore power immediately. The storm is ongoing. The conditions that caused the problem are still present. Reconnecting equipment while the geomagnetic storm continues could cause further damage, so operators have to wait. They have to watch and monitor until the storm subsides, until the induced currents decrease to safe levels. Only then can they begin systematically restoring the grid. That waiting period could be hours. It could be days if the storm is particularly severe, or if multiple CMEs arrive in sequence, keeping geomagnetic conditions disturbed for an extended period. And remember, this isn't a localized outage affecting one city or region. A major geomagnetic storm affects large geographic areas simultaneously. We could be talking about outages across multiple states or provinces, millions of people without power, all at once, for an extended duration. Think about what happens during an extended power outage. No refrigeration, food spoils, no heating or cooling systems. In winter, that's life-threatening in northern latitudes. In summer, it's dangerous for vulnerable populations. No water pumping in many systems because electric pumps provide water pressure. No fuel pumps at gas stations, so even if you have a generator, you can't easily refuel it. Communication systems run on battery backup for a while, but when those batteries drain, cell towers go offline. And without cell service or internet, coordinating response efforts becomes exponentially harder. Hospitals have backup generators, yes, but they're designed for temporary outages lasting hours to perhaps a day or two. If an outage extends beyond that, fuel supplies for the generators become critical. And remember, fuel trucks can't navigate easily if traffic lights are out and GPS is unreliable. The logistics of providing fuel to thousands of critical facilities across a storm-affected region during an extended outage would be a nightmare. I'm painting this scenario not because it's likely with the current storms from AR4324 and AR4325. The predictions for those events were minor to moderate, remember, but I'm painting it because it's possible. It's within the range of what the sun can do, it's happened before in different forms, and it's helpful to understand the potential worst-case scenarios so we can appreciate both the risks and the precautions that are being taken. Aviation is another area of vulnerability. High-frequency radio communications, which airlines use to communicate with aircraft over oceanic routes where radar coverage doesn't exist, can be completely disrupted during strong geomagnetic storms. When pilots can't communicate reliably, they have to implement backup procedures. That might mean flying at lower, less fuel-efficient altitudes where other communication methods work. It might mean avoiding polar routes entirely, where both communications and GPS are most affected. All of this means delays, cancellations, increased costs, and inconvenience for travelers. Space agencies worry about their assets in orbit. The International Space Station, with astronauts aboard, has protocols for geomagnetic storms. The crew can move to more shielded areas of the station during the most intense periods of particle bombardment. Satellites that can be commanded into safe modes are put into those modes to minimize risk, but there's only so much you can do. Satellites in orbit are exposed, some will be damaged, some might be lost entirely, and then there's the internet. The physical infrastructure of the internet is more resilient to geomagnetic storms than power grids because the cables themselves are less affected by induced currents. But the internet depends on power. If data centers lose power, if major internet exchange points go offline, portions of the internet become unreachable. Cloud services fail, websites go down. The modern economy, which runs largely on digital infrastructure, grinds toward a halt. The economic cost of a severe geomagnetic storm is difficult to calculate precisely, but studies have attempted estimates. For a Carrington-level event striking today, some estimates range into the trillions over the years needed for full recovery. That's because the damage isn't just immediate. It's not just the cost of replacing damaged transformers or satellites, it's the cascade of economic effects, lost productivity, disrupted supply chains, food spoilage, medical care disruptions, all the ways that an extended infrastructure outage ripples through a complex modern economy. But here's the crucial thing to understand. We're not helpless. We're not passive victims waiting for the sun to destroy our civilization. We've learned from past storms, we've built monitoring systems, we've improved forecasting, we've developed protocols and procedures. Power grid operators know how to respond to geomagnetic storms. They can adjust operations to minimize risk. They can disconnect vulnerable transformers preemptively if conditions warrant. Satellite operators have hardened their spacecraft designs and developed operational procedures for storm periods. Airlines have backup communication methods. We've adapted. The storms from AR4324 and AR4325 are tests of those adaptations. They're not the big one. They're not Carrington Redux. But they're real events happening in real time, and they give us opportunities to practice, to refine our responses, to identify weaknesses in our systems before a truly major storm strikes. And make no mistake, a truly major storm will strike eventually. Not might. Will. It's not a question of if, but when. The sun will produce another Carrington-level event. It might be this solar cycle. It might be the next. It might be 50 years from now. But it will happen because the sun is capable of it, and given enough time, all possible solar events become probable. So when I walk you through these worst-case scenarios, I'm not trying to keep you awake at night. I'm trying to give you perspective. The current storms are manageable. They're within the range of what we've experienced and handled before. But they're also reminders, warnings perhaps, that we live in a universe that doesn't care about our infrastructure or our convenience, that the sun is a nuclear furnace that occasionally hurls material our way, and that maintaining our technological civilization requires constant vigilance and adaptation to forces far beyond our control. Now let's talk about the silver lining, because even though geomagnetic storms can cause problems, they also create something beautiful. For all the technical concerns, for all the infrastructure vulnerabilities, there's one effect of geomagnetic storms that humanity has appreciated for thousands of years: the aurora. Those shimmering curtains of light that dance across polar skies, painted in greens and reds and purples. They're not just beautiful, they're proof of the invisible battle being waged in Earth's upper atmosphere. They're the visible manifestation of our planet's magnetic shield responding to solar material, and they're absolutely mesmerizing. When solar particles funnel along Earth's magnetic field lines toward the poles, when they collide with atmospheric molecules at high altitude, energy is transferred. Oxygen atoms, when excited by these collisions, emit green and red light. Nitrogen produces purples and blues. The specific colors depend on which atoms are being excited and at what altitude the collisions occur. Higher altitude collisions tend toward red. Lower altitude collisions tend toward green. The result is a light show that no human technology can replicate. No fireworks display, no laser show, no special effects come close to the ethereal beauty of a strong auroral display. For people living in far northern regions, aurora is a regular occurrence. It's part of life. Alaskans see it frequently during winter months. Northern Canadians are familiar with the lights. Scandinavians have built entire tourism industries around aurora viewing. But the aurora typically stays at high latitudes. It hugs the Arctic Circle. Most people living in mid-latitude regions never see it in their entire lives. It's something they might travel to witness, a bucket list item, but not something they expect to see from their own backyard. That changes during geomagnetic storms. When Earth's magnetic field is disturbed, when it's compressed and distorted by incoming CMEs, the aurora expands. It pushes toward lower latitudes. The stronger the storm, the farther south it reaches. During G1 storms, aurora might be visible slightly south of its normal range. During G2 storms, it can push into mid-latitudes, appearing across the northern United States and Central Europe. During G3 and stronger storms, people in places that almost never see aurora can witness it. Reports come in from unexpected locations. People step outside and see lights in the sky they've never imagined they'd witness from their home. The predictions for the storms from AR4324 and AR4325 suggested this possibility. G1 to G2 conditions meant aurora could be visible well south of typical viewing areas. For people living in northern states, across Canada, in northern Europe, this was a chance to see the lights without travelling to the Arctic, and Aurora forecasting communities erupted with excitement. Social media filled with posts about where and when to look. Photography groups prepared their equipment. People who had never seen Aurora in person suddenly had an opportunity. There's something profound about witnessing Aurora. It's not like watching a sunset or a lightning storm. Those are familiar atmospheric phenomena, weather that we understand and experience regularly. Aurora is different. It's ethereal, otherworldly. The lights move in ways that seem almost alive, rippling and flowing and pulsing. They can cover vast stretches of sky, or concentrate in narrow bands. They can last for minutes or hours. And the experience of standing beneath them, watching them dance overhead, creates a connection to something larger. You're witnessing the interaction between your planet and your star. You're seeing evidence of forces that operate on cosmic scales, forces that are usually completely invisible to human perception. Photographers love Aurora because it's both stunning and challenging to capture. The lights move constantly, which means long exposures can blur the details, but short exposures might not gather enough light to show the colours properly. Finding the balance requires skill and experience, and the best Aurora images, the ones that truly capture the drama and beauty, require not just technical ability but timing and luck. Being in the right place when the storm intensifies, having clear skies. Having the aurora appear in the right direction relative to your position. For scientists, Aurora is data. It's a natural laboratory for studying the interaction between solar particles and Earth's atmosphere. Different colours indicate different processes at different altitudes. The structure and movement of auroral forms reveal information about how energy flows through Earth's magnetosphere. Citizen scientists around the world contribute observations, photographs, reports that help researchers understand the details of individual storm events. What might seem like simple appreciation of natural beauty actually contributes to the scientific understanding of space weather. But for most people, Aurora is simply awe. It's wonder. It's one of those rare experiences that makes you feel small in the best possible way. Small not in an intimidating sense, but in a perspective-granting sense. You're watching something that your ancestors watched. Indigenous peoples across the Arctic developed myths and stories to explain the lights. Some cultures saw them as spirits of the dead, others as dancing animals or warriors. Every culture that lived where Aurora was visible created meaning around the phenomenon. And even now, in our scientific age when we understand the physics behind the lights, Aurora still evokes that same sense of wonder. So as those CMEs approached Earth, as scientists monitored storm predictions and power grid operators prepared for possible disruptions, there was also a community of people preparing differently. They were checking weather forecasts, hoping for clear skies. They were identifying dark locations away from city lights. They were charging camera batteries and planning late-night vigils, because they knew that when the storm hit, when Earth's magnetic field began to respond, there was a chance they'd witness something extraordinary. And that's the duality of geomagnetic storms. They're technical challenges for our infrastructure. They're potential sources of disruption and damage, but they're also opportunities to witness nature at its most spectacular. The same process that threatens satellites and power grids also paints the sky with light. The same particles that cause problems also create beauty. It's a reminder that the universe is neutral. Events aren't inherently good or bad, they simply are. It's our response to them, our preparation and our appreciation that determines how we experience them. So while engineers monitored grid stability and satellite operators checked systems, Aurora chasers pointed their cameras skyward and waited. Both responses are valid, both are appropriate, because a geomagnetic storm is both a challenge and a gift depending on your perspective. So where does that leave us? Right here, right now, in the early days of a new year, with our planet having just been struck by solar storms launched from 2 active regions on the Sun's surface. By the time you're watching this, the CMEs have likely arrived. The geomagnetic storm has occurred or is occurring. We have data, we have results. We know what actually happened rather than what was predicted might happen. And for those of you watching this in the future, you know how this particular story resolved. You know whether the predictions held, whether the storms were stronger or weaker than expected, whether any systems were significantly affected. But regardless of the specific outcome of these particular storms, the larger story continues. Because AR4324 and AR4325 are not isolated anomalies, they're symptoms of a sun that's approaching the peak of its activity cycle. We're nearing solar maximum, that period roughly every 11 years, when the sun's magnetic field is at its most complex and unstable, when sunspots are most numerous, when flares and CMEs are most frequent. We've entered a period, lasting months to potentially years, when we should expect more events like this. Not every day, not every week, but regularly enough that space weather becomes a routine consideration rather than a rare concern. Those two sunspot regions are still rotating across the sun's face right now. They haven't disappeared. They haven't stopped being active. As long as they remain visible from Earth, as long as they continue facing our direction, they retain the potential to produce additional eruptions. Scientists are monitoring them continuously, watching for signs of new flares, new CMEs. If they erupt again while still Earth-facing, we'll go through this process again. Predictions, preparations, waiting for impact. It's a cycle that could repeat multiple times as these regions traverse the visible solar disk. And beyond these specific regions, the sun will continue producing new sunspots. New active regions will emerge on the eastern limb, rotate into view, face Earth, and potentially erupt. It's the nature of solar maximum. The sun is restless. Its magnetic field is tangled and stressed. Energy is constantly being released. Some of that energy will be directed at Earth. Some will miss us entirely. But over the months ahead, we're guaranteed to experience multiple geomagnetic storms, some minor, some moderate, and possibly, if the statistics of solar activity hold, at least 1 or 2 major events before this cycle peaks and begins declining. That's not a threat. It's not fear-mongering. It's simple observation of how the sun behaves. We've watched it through multiple cycles now. We understand the patterns, and we know that solar maximum is when space weather becomes most interesting, most challenging, and most beautiful. More aurora displays at lower latitudes, more disruptions to technology, more opportunities to test our systems and our preparedness. More reminders that we live not in isolation but as part of a dynamic system that includes our star. So what should you do with this information? Should you worry? Should you prepare for disaster? Should you build a bunker and stock supplies? No, that's not the message here. The message is awareness, understanding that space weather is real, that it affects us, that it's not something that only matters to scientists and engineers. The technology you use every day, the infrastructure you depend on, exists in an environment subject to forces from space. Being aware of that, understanding it even at a basic level, makes you a more informed person. It gives you context when you hear about geomagnetic storm warnings in the news. It helps you understand why aurora might suddenly be visible from your location. It connects you to the larger cosmic environment we inhabit. If you want to stay informed about ongoing space weather, resources exist. The Space Weather Prediction Center, operated by NOAA in the United States, provides continuous monitoring and forecasting. They issue watches and warnings when appropriate. They publish data and explanations accessible to the general public. Similar agencies exist in other countries. Aurora forecasting websites and apps can alert you when conditions favor auroral displays in your area. If you're a photographer or just someone who appreciates natural beauty, following these resources means you won't miss opportunities to witness the lights. For those in industries affected by space weather, the key is preparation and adaptation. Power grid operators already monitor space weather as part of routine operations. Satellite companies build hardening and redundancy into their systems. Airlines have protocols for communications disruptions. The systems exist. The challenge is continuous improvement, learning from each event, identifying vulnerabilities before they are catastrophically exposed. Each moderate storm is practice for the major one that will eventually come, and that major one will come. Maybe not this year, maybe not this solar cycle, but eventually Earth will be struck by another Carrington-level event or possibly something even stronger. When that happens, our response will depend on how well we've prepared, how much we've learned from smaller events, how robust we've made our infrastructure. The sun doesn't give us a choice about whether these storms will occur. It only gives us the choice of whether we'll be ready when they do. But in the meantime, in the months and years ahead as this solar cycle progresses, we get to live through something extraordinary. We get to witness our star at its most active. We get to experience space weather as a present, ongoing phenomenon rather than an abstract concept. We get opportunities to see aurora from places it rarely appears. We get to watch scientists refine their forecasting. We get to observe how our technological civilization adapts to forces from space. It's a privilege, really, to live in an age when we understand these processes, when we can predict them, at least somewhat, when we can appreciate them both scientifically and aesthetically. So as we close this exploration of the storms from AR4324 and AR4325, as we transition from discussing these specific events to contemplating the broader picture, I want you to take away one central idea. You live on a planet orbiting a star, not a gentle, predictable star, but an active nuclear reactor that regularly releases massive amounts of energy. That star can affect your life in ways you probably never considered before watching this video, but humanity has adapted. We've built systems to monitor and predict. We've developed resilience and redundancy. We've learned from past events, and we continue learning with each new storm. You're part of that story now. By watching this, by understanding even a fraction of what's happening above you, you've joined the community of people who look up and see not just a sky, but a dynamic interface between Earth and space, who understand that invisible forces are constantly at work, who appreciate that our technological civilization exists in a precarious balance with natural forces far beyond our control. That awareness doesn't require you to do anything different in your daily life, but it might change how you see that daily life. It might create a sense of connection to something larger, and that ultimately is what understanding space weather is really about. If this video has expanded your perspective, if you found value in this journey through solar storms and geomagnetic effects, do me a favor, share it. Not because I need the views, though that certainly helps, but because this information is worth spreading. Most people have no idea this is happening. Most people don't understand the connection between sunspots and their GPS, between solar eruptions and power grids, between cosmic events and everyday technology. By sharing this, you're helping build a more informed community, a group of people who understand that we're not separate from the cosmos, but intimately connected to it. And stay subscribed. Because this story continues, as AR4324 and AR4325 evolve, as new sunspot regions emerge, as the solar cycle progresses toward its peak, I'll be here covering the major events, translating the science, explaining the implications, celebrating the aurora. This is an ongoing conversation between humanity and our star, and you're invited to be part of it. Drop a comment below if you're still with me. Tell me where you're watching from. Tell me if you've ever seen aurora in person. Tell me what aspect of this topic fascinates you most. Build that community with me, because space weather affects all of us, together, under the same sun. And understanding it, preparing for it and appreciating it is something we can do collectively. The sun will continue erupting. CMEs will continue racing toward Earth, geomagnetic storms will continue testing our systems, and aurora will continue painting the sky. That's the reality of living on this planet at this time in history. But now you understand it, you're aware, you're informed, and that makes all the difference.